Alright, greeting Physics 2. I wanted to give you a quick video review and midterm review, particularly what I did with my other classes, just so we're all on the same page since I know the midterm is coming up, and I wanted to send this out to you before, obviously, the midterm, so you could have another chance to review some of the stuff, especially some of the assignments that I did give out. First, a couple questions that I'm assuming you have is the equation sheet. So, just a reminder for the equation sheet, you are going to bring it. And that, most importantly, that it's just equations, that it's not any sort of definitions, it's not diagrams, it's not drawings, it's not units. So it just has to be equations. So I was telling my other classes that since I think the biggest thing that, people struggle with the midterm specifically is not so much the calculations, but messing up the relationships between the calculations. For example, you'll see in a moment, I'm going to go through some of those equations, is that you'll see a velocity final in linear motion, and then you see velocity final in free fall, but you can't use them for the same question because one model's straight line and one model's falling. So that's what I see a lot of times in midterms. So, just to show you what you could do with your equation sheet as well, if you remember, back in like September, we did things like displacement and distance, right? So displacement is final position minus the initial position. So what you can write on your equation sheet is delta x is equal to displacement. You can write that. What you cannot write is that usually displacement is in meters. So just like delta x equals displacement. You could write xi is equal to initial position and then you could write xf is equal to final position. As such. So you can write that. And notice there's no units. You may use your old equation sheets, it's totally fine, but the problem is if you have units, you must either white them out or use a black marker or a dark marker to kind of X those out. So if you remember, distance is the sum of any legs of distance that you have. So remember, this symbol means sum here, and you can actually define that. I don't mind that, sum. And remember, these are the different legs. So if you had like it goes forward and then goes backwards and then goes forward again, that's what these x's represent. So you could x equals different positions. Like that. But also remember that we did have speed as being total distance over total time, and then we had velocity as displacement over time, so slightly different like that. And then we had acceleration for linear motion as v final minus v initial over t. So this is all linear motion, LM, linear motion. So I would, if I were you, I would actually color coordinate this, color coordinate this. I'm just going to hide this and just, okay, that's all my linear motion, but my free fall equations, maybe do all in red. You could do whatever color or organizational way you like, but notice why I'm stressing this, because notice you have a VF final here. This is one of your equations. Then you have delta x VIT plus 1/2 GT squared. And then you have this one. So what I see a lot in the midterm is that, oh, look, you have a VF here. I could find acceleration. Or I can find the initial speed here, and vice versa. Now, you can't, because this is modeling something that's falling, going down, and this is modeling something that's on a road or going straight or something like that. So just know that those are two different scenarios. I see that, again, a lot. It's just people mixing up the scenarios. So make sure you kind of either box them off or kind of treat them as different things because they model different things. Now you may put constants on your equation sheet, like the following that I have here. G is G is 9.81 meters per second squared. So that's where units can come in. So you can put units with your constants. And remember with free fall, although you can't write this on your equation sheet, but remember to make g negative because you have to model direction with free fall. So I'm just going to put this in a box as a side note. So remember, modeling direction, you have to use 9.81 as negative. Now in other cases you don't model direction, and we use the positive value, and that's for specifically like energy, because we don't really care about the, well, I mean, we might care about direction, but we're looking at values, not direction. So just careful when you're modeling your directional pieces. And just to be repetitive, remember that you always want to make the free fall equations negative 9.81. You don't want to take that sign out. But remember, you can't actually use this on your equation sheet because that does actually change, and you just have to be careful with that. So the next thing that we did after free fall is we did Newton's laws. So let's take it right here. I'll change the color like that. And then we did Newton's laws. So I'm just quickly going over the concepts. So remember, Newton's first law is the law of inertia, which says the object will keep doing what it's doing. So more about the application. Newton's second law is F equals ma. You're kind of looking at after the fact that if you have a net force, your forces are not balanced, the object will accelerate. And then Newton's third law is the action-reaction, that every force is the same, but if you have different masses, you'll undergo different accelerations. So that's the basis of Newton's laws right here. Now, the equations that we did, so I'm just going to box this because you can't have this on your equation sheet. These are the no-nos. But things that we did do is weight, for example. So if you want the weight of the object, that's Fg. This is when defining this is kind of important. So if you want to know how something weighs, it's going to be mass times g, which is 9.81. Now you can find the mass of something by rearranging this equation, just taking the weight of the object and dividing by g, which is helpful. So you can find mass or weight given one of the two right here. That's one set of equations we used, and the other set really is just F equals ma, so F net equals ma. And then the other equation we did is the net acceleration, so which is the net force divided by the mass, like that. So just another warning, and this was on the exam too, is just remember we have two ways to find mass. It actually doesn't matter which one you use, but you have to use the right information. So what I mean by that is the net force, if you're going to find the mass with the net force, you have to have the acceleration. If you want to find mass with gravity, you have to use the force of gravity. So you can't use net force in place of gravity and etc. like that. So just be careful with that assumption that you make here. And that was something I did notice on the most recent exam. So again, just be careful with what you use. And then after that, we did circular motion. And if you recall circular motion, we can find the speed of an object going in circular motion with 2 pi r over t. But again, this velocity looks just like linear velocity. So you have to ask yourself, is it going in a straight line or is it going in a circle? Because people confuse that as well. And this capital T is period. It's not any time. It's a time for one circle. Period. I'm going to put the unit here. You're not allowed to do that, but period has to be in seconds. So if I give you a period in minutes or hours, you must convert that to seconds. And that is a very special type of time. It's not just any time. Oops, sorry. And then we did two other things. We did... sorry, my mouse is being weird for whatever reason. We should be okay now, maybe. We did centripetal acceleration is v squared over r. I don't know why my mouse is all weird right now. And then we did force centripetal is equal to mv squared over r. Like that. So that was the other thing that we did. Okay, I'm back. Sorry, there was a quick glitch with my pen, and I fixed it, I think, so hopefully we can keep going. So like I said, with circular motion, Just going to be repetitive once again. So this is for objects moving in circles. Remember that if you're moving in a circle, you find the velocity of the object this way, not with this one, just a side note, because this is for objects going in a straight line. We don't want to use that, okay? And then we did frequency and period. So remember, frequency is the number of cycles or revolutions. It doesn't matter which one you use, over time. And then period is the opposite. It's time over a number of cycles. So there you go, like that. And these are inversely related, so in other words, if you know one, you can get the other by taking the inverse. Sorry. Let's go back a little bit and just do this. Yeah, so that's all circular motion. The good news is gravitation is just gravitation. It's just a force-gravity equation. Now I recommend that you check your calculators to see if this is already programmed in before your midterm, and that if it isn't, that you find someone that can help you do it, or you let me know and I can help you with it. You can write this down because this is a constant, which is the gravitational constant, force constant. Like that, there you go. And just some quick things about modeling this. Remember that these are two different masses, M1 and M2. Doesn't matter their size. And that R is the distance between the two of them. And the force of gravity that you calculate from this between the two objects are the same and pointing inward. My arrows should be the same. It's just really sloppy like that. Like that. So that's gravitation. And then lastly, the things that we've been working on, no pun intended, is work. Where work is force times distance. And remember that when you do work is force times distance, that work is not always calculated this way. You can have zero work. This is not permitted on the equation sheet. But I just want to say that the two conditions is, remember, when the force is perpendicular, or if either force or distance are zero. So sometimes you don't even have to calculate this value. But in most cases you will if you have a force and a distance. Now when you're lifting something or running upstairs, you're lifting your body, and you have to take the mass and make it into a force. So it's mg times d like this. So that's again for stairs or for lifting. So if it gives you a mass, you must multiply by 9.8 to make it a force. But if they just give you a force, then you don't really need to do anything. So that's the good news with that. Now power is how much work you do over time. So if you know the value of work, you can divide that by time. And remember that time must be in seconds. Again, you can't have seconds on your equation sheet, but I'm just reminding you that if you have something like hours, you have to convert. Now you can have other conversions on here, like there are 3,600 seconds in 1 hour. It's a helpful one. Or there's in 1 minute, there's 60 seconds. You can have all of this. This is just nice to remember to help you with converting things if you need to. You can have as many conversions as you want. You don't need to, hold back on that. And these obviously can have the units because you need units for conversions. But you can't and will not have this permitted. As always, I'll take a look at your equation sheets beforehand, which is super helpful with that. After work, we did types of energy, so recognizing the types of energy. So we had energy associated with motion or kinetic energy, energy associated with stretching, elastic potential energy. We had energy associated with height or position, called GPE, like that. So in short, this is velocity, this is related to height, and this is related to stretch. And as always, everything is measured in joules. Again, you can't put that in the equation sheet, but recognizing that anytime you have motion, that's kinetic, position, that's gravitational, and stretch, that's elastic. And then the last thing we learned is to say that if there's no work done on the system, in other words, there's no force from friction or force from pushing, that the total energy before has to equal the total energy after. Now this is very arbitrary written because it could be displayed in many different ways for many different situations. So, for example, we did something like this where we had a roller coaster and it did this, and I think this is one of your questions. So if you have full potential at the top, and no kinetic. Now it's all potential because this is all height based. So if you're at the top here and you're at rest, then this is your energy. But at the bottom right here, since you have no height, this would be 0. And then basically says with no work. So if there's no friction in this, let's assume that's the case, then all of the energy here goes into the energy here. That's conservation of energy. So you will be using these bar graphs, which we've done in class. There's actually a video on this too, which I'll show you where to find. Like that. So you should be able to fill in these bar graphs, right? So there's a half, there's a whole, equals that, and these should be somewhat equal. This doesn't pertain to any situation, so just like FYI, but being able to do that. So because I have a whole video solving this, I'm not going to solve it here, but that's another concept like that. So speaking of, let me actually take a step back here and actually do the following. Let's do, I want to show you that if you go to topics, midterms, practice. If you go to midterm practice, you'll be able to download the midterm practice exam. And this is how you'll see the practice. You'll have questions, except this is going to say 20, not 10. You have 4 questions. Now the first one right here, you're going to have 2 motions. It's not necessarily going to be circular and linear. It could be free fall, it could be displacement, it could be gravitation, it could be one of the 2 cases, but you're going to calculate some of these values. So whether it's speed, time, force, velocity, I'm just going to say which one has more for each of those cases. So you have 1 calculation question. So of the maybe 20 equations you have, you may only use 3. So that's on purpose. The next question is a lab question. So this is a lab we didn't do, but the question on your midterm will be a lab that we did do. So for example, acceleration, we took a ball, we put it on a ramp, we segmented the distances into equal increments, then we measured the time it took to get to each of those distances, and then we graphed the displacement in time, and we found that if it curved, it was accelerating. So that's kind of the idea of this question. Do you recall and understand your labs? This one, you're going to have 2 questions in argumentation. 3 people will say something. You're going to tell me if you agree or disagree with them. You'll have 2 of those questions. And then this is exactly how I'll present energy. So I'll give you a scenario. You have to fill in the bar graph and tell me a little bit about why you did the bar graph as you did. And then you're going to use conservation of energy to solve for this part right here. Then we're going to change the bar graph and calculate power. So that's the way you're going to see energy on this exam. So all the solutions are right here on the bottom. There you go. So I recommend that you try this on your own, and then of course use the solutions to kind of help you with how to do it. Also, if you click on the link below, I'll just do it, the review, you come across this right here. Now the review will show you exactly what we did in class. So which labs we did, what we highlighted, the equations, all that fun stuff is all right here for you. Oh, excuse me. So I got cut off for no reason, but I'm just going to go back to the top just in case. So this is the midterm review. This is just showing you that this is what we've done throughout the year, and I kind of laid it out for you, including all the labs, the conditions, some of the big ideas. It's all right here to help you study. So I recommend going over this, your old tests, to help you practice some of this information out. There's a video right here, and these are all just additional practices from everything else too. Especially for those who are worried about conservation of energy, there's more energy practice for you if you need some more. I like this one if you go under it because it's perfect. You fill in the blanks. What do I know about units? How do I solve these questions? There's just more work for you to help solve extra things. And I'm just going to give some feedback on the quiz for my last part of the video, just because I wasn't able to do it in class. So the quiz was totally completion based, so regardless of your score, I'm going to give you full credit for it. It does count as a test score, so you're welcome. But let me just talk about some of the questions you may have had, since these are common issues that I heard in the other classes. So first of all, there was a couple glitches in the exam, so I'll talk about what those are in a second, but if your score might be lower than what it should be anyway, which is why it's good that it's a completion grade. But this is one of the questions on the quiz, and these were some of the questions that people had. So this one right here said, what's the kinetic energy of the skier? And although most of you are correct to say that, it's probably going to be less, it's technically you cannot determine, because it could actually be 0, depending on how much friction. So you really can't tell how much the kinetic energy goes down. Now, there are other parts to this, but, in part, I'll just summarize. Part B, the potential goes down because you're definitely losing height. And for part C, the TME goes down because you're losing energy due to friction. So that's the kind of the idea of this question. But I want to do this question specifically because it's very similar to what you'll see in your midterm anyway. But here we go. If you had no friction, what's the total energy at the top? So you're going to have all potential energy because the energy at the top is going to be associated with the height, and you're at rest. So it's all GPE. So the GPE is going to be mass of the person times 9.81 times the height. So all of you probably have different masses here. Let me just grab the calculator. Here we go. This is how you do this part right here. 66.35 times 9.81 times 8.21. And when you calculate this, you get 5,343.83 joules of energy. So that's the potential energy at the top of the hill. Assuming no friction, how fast is the speeder, how fast are you going at the bottom? So if you notice that, let me just add a text box here. At the top, you have two forms of energy. You have potential and you have kinetic. Well, at the top, the kinetic is 0 because you're at rest. And at the bottom, at the top, you have this much because this is what we calculated. Now at the bottom, what's happening is, at the bottom, you have no height anymore. So you have no potential energy. So, according to conservation of energy, and since there's no friction, all the energy at the top must equal the bottom. So if that's the case, you have all kinetic energy at the bottom, which means that we can find how fast you're going. We can do that by saying KE is 1/2 mv squared. And I hope you know that that is in fact squared. So that means all of the energy that we had at the top is equal to the bottom, and we do 1/2, and then the m is 66.35 with this question, and you're solving for v squared. So v, I'm just going to solve for v squared, so it's going to be times 2 divided by mass, and then I'm square rooting the answer. 12.69 meters per second is the velocity at the bottom. Just like that. So you have a similar question on your exam, except it will be one question. It's the bottom of the hill, so you need to go through this to get to that. So it's a two-parter, just like that. So that's the feedback on this question. Now the feedback in this question is, you know, for A, just because I'll just add it in there, part A, the answer for that missing piece is 40,000, which everyone did just fine. For location 2, it should be 40,000. I think it marked it wrong for whatever reason, but the answer is 40,000 because you have all the energy here and no height. And in fact, that gives you the reason why location 3 is in fact 0, because you have no height. So that was a glitch on the problem. So if you wrote this, you were actually correct with that. And then finding the height for part A comes from looking at the diagram. Height comes from GPE, MGH. So at part A, the energy there was 40,000. All of the energy is equal to m v squared. Now, I didn't write down the m here, but your m should be something like, I used 312 for one class, so 312 kilograms times 9.81 times h. So I'm solving for h here. 40,000 divided by 312 divided by 9.81, so the height is 13.0, around 7 meters. So that's how you find the height. You take the energy at the top and you apply the energy equation. And then same thing, the velocity for part B, so the velocity here for part B. So the energy there from a previous question is 20,000 because it has to equal to 40,000. So that's because the total energy has to remain constant. So the energy at that location is 20,000. And then we're going to do is similar to what we just did, is say that the kinetic energy is equal to 1/2 mv squared. I'm just going to be lazy and just do this. So the new energy becomes 20,000 joules, and then the mass is 312. Now I'm using 312 because that's the mass that was given in my question. I didn't write it down here if you notice, so it depends on your mass. So obviously you use whatever mass you use. And then V, solving for that, would be 20,000 times 2 divided by 312, square root the answer. 11.32 meters per second. There you go. And that's how you can find the velocity at the bottom of your incline like that. So if you have any more questions, just let me know. I think most of you did just fine otherwise on all the assignments. I will be updating or have already updated your grades, so just give me a heads up. And best of luck on your midterm.